but in any case, good. So, as final part of this course, this season, I try to answer the question, and that's what this whole session today is about, picking up essentially from the last session. The question is, what is the relation between maximum statistics and family-wise error rate, or these p-values, which are called family-wise error corrected, although they are not corrected p-values. So the maximum statistics we're talking about are the distribution of the maximum of the random field. So I think we call that xm, and that is the peak level in SPM, the peak level PFE corrected, and the other one I think we call it KM, which is the cluster size or cluster level PFWE corrected. Yeah, so this is for the value of the statistic of the SPM. So there are these different values encoded for each voxel, and they have a certain size, and then depending on how high this value is, there is a p-value associated with it, and one of them is called PFWE corrected, and the same thing for the cluster size. As we discussed, there's the distribution of the maximum cluster size, and this is called the PFWE corrected p-value. And as I also discussed last time already, there is one thing is to know what these p-values are and what distributions, where they come from, and the other thing is the question of what they have to do with family-wise error rate, or in other terms, what they have to do with statistical testing. Because this is the strange thing that p-values, on the one hand, they can be used for statistical testing, but they can also not be used for statistical testing, just as a summary of noise, signal-to-noise ratio. In any case, that's the question, and so we started that last time when we discussed what a t-test is, essentially, and then started out on some formalization of statistical tests. And the plan for today is then to go a little bit quicker, again, over the single test scenario. I changed a little bit of the notation here and there, so I think it might be good to first revise again the single test scenario, then go to the multiple testing scenario, and then see how maximum-based statistics help for FWE are controlled. Yeah, so that's the plan. And since there are no master students today, we can go quickly, and I don't want to so no intuition. So, was there a question? No? Good. So the question is really why are some of these columns in the SPM table labeled PFWE corrected? The labeling is wrong and confusing, but the question nevertheless is there of why this is done. And yeah, this is what I want to discuss. And here we go. We start with the single test scenario. And last time we reminded ourselves how a typical test looks like, namely the t-test. And so now we can go quickly again to remind ourselves what's going on. And first thing, so we will basically just go over a lot of definitions. So first thing, data sample and parametric statistical model. So over the week I introduced the notion of a data sample because it makes things a little bit easier to have that explicitly defined. So the way the whole thing works in terms of probability theoretic concepts is that there is a family of probability spaces, omega R, which is the sigma algebra on omega, and the family is given by this family of probability measures, p theta, where theta is in some parameter space. So that's a family of probability spaces, and it's a family because there are many probability measures. And of course, for one fixed small theta and theta, p theta is a probability measure on the sigma algebra, and the big theta is referred to as parameter space. A data sample is then given if we consider another measurable space. So let y F denote another measurable space. Y is the outcome space of the data. Then a data sample is a random variable y from omega to, maybe I should do this with a double, something like this. Is a random variable, which means it takes one omega in the underlying probability space and maps that onto a value in the data outcome space. And if this is the case, so if we have this family of probability spaces and we have this random variable called data sample, then we have, and this is what we had last time already, then we have a parametric statistical model where we have the data outcome space, the sigma algebra over this outcome space, and this collection of family of distributions of the data sample, which is parameterized. And this is called parametric statistical model, PS, parametric statistical model. So typical example for this is of course the GLM, where you have the case that the probability distribution of the data is given by a normal distribution, which is parameterized in terms of beta parameters and either variance parameter or, in fact, in SPM implementations, covariance component parameters. Yeah, so this is a typical example for a parametric statistical model, and this is just the abstraction or generalization of that. Good. And of course, it doesn't mean much. It just means that there's some outcome space. And of course, the outcome space depends on what you're trying to model. So if you're modeling the whole brain volume, then the outcome space is like a 3D volume of many, many voxels. If you're modeling a single voxel, then the outcome space is a n-dimensional vector space. If you, I don't know, if you're doing some social psychology experiment, then the outcome space is something like, I don't know what they do in social psychology, but that's just a very general framing of a typical parametric modeling framework. Good. Now for hypothesis testing, we've already also seen last time that that the crucial thing in hypothesis testing is, of course, hypotheses are, of course, hypotheses. So, and we already seen last time, maybe I should underline this, it's nicer. Hypotheses are, there are two always in this typical hypothesis testing framework, namely the null hypothesis and the alternative hypothesis. This is all Nyman Pearson style hypothesis testing, where you have a null hypothesis, you have an alternative hypothesis, and you can talk about things like power. This is not where you don't have these things and cannot talk about them, like Fisher, but this is Nyman Pearson. The fundamental thing is that you have the parameter space, and then you do a bipartition of parameter space into what is called the null hypothesis, which is one part of a parameter space. It's not empty, otherwise the whole thing wouldn't help. And theta 1, which is defined as the complement of theta 0, so theta without theta 0. Yeah? And this is called null hypothesis. This is called alternative hypothesis. So one can, so the real statement of the null hypothesis, if you want, is that the true but unknown parameter theta is an element of the subpart of parameter space that is called null hypothesis. Like last time, we identify the statement that the true but unknown parameter is in theta 0. We identify theta 0 with the statement null hypothesis. So again, a typical thing in terms of, let's say, one sample t-test is that the true but unknown parameter of a normal distribution mu is, for example, is an element of the set 0, meaning the null hypothesis is in the both terms that the expectation parameter is 0, and the alternative hypothesis that is that mu is a real value not in 0, so some other value. But of course one can also in this framing of hypothesis can also for example say that mu is some negative real number, for example, and then the alternative hypothesis it's a positive real number. So one has a lot of flexibility when framing null hypothesis and alternative hypotheses this way. Good. So these are hypotheses. Simply the bipartition of parameter space is a hypothesis, which in my opinion is kind of already the breaking point of the whole hypothesis testing framework, because it throws away all the information that you have in terms of parameter estimation, and so forgoes in terms of what you actually estimate, and then says it's only roughly where it is. So I'm not a big fan of hypothesis testing, but I think this is obvious anyway. So then the next thing is single test problem. Also we had that last time. Single test problem is the typical null hypothesis testing problem everyone is familiar with. In our language, this is given by a parametric statistical model. So we have the outcome space of the data, the sigma algebra over this outcome space, the family of distributions of the data, and the a set of hypotheses. And the crucial thing about the single testing problem is that the set of hypotheses, here this strange H, is that it contains a single null hypothesis. Hence a single testing problem, or a single test problem. Because for multiple tests we will have multiple null hypotheses. Good. Then statistical test. The typical definition of a statistical test is given in the scenario of a statistical parametric model, and there are different ways to frame that. So the important thing is that we have this data sample, which is a random variable, so y from omega to the outcome space. And the test is, of course, acting as a function on the random variable data, which is not surprising. So you first sample some data, and then you apply your test procedure to that data, and the test procedure is deterministic. So in most cases, of course, you can also come up with randomized tests, but the normal thing that we are familiar with in terms of t-test, f-test, or z-test, that's deterministic. So you sample some data, and then you, like we did last time, then you compute the mean, compute the expectation parameter estimate, the variance parameter estimate, the t-value, then compare that to some critical value. But all these steps are deterministic, and the randomness comes in terms of the test outcome comes in because the data are random. So one can hence write a statistical test if one wants, like this. So it also takes elements of the underlying elementary outcome space and maps these into 0, 1. And it, of course, only indirectly acts on the elementary outcomes because it acts on what the data sample does with these elementary outcomes. The question is, and the only thing why I'm doing is that one doesn't get confused about which distributions actually govern the outcome, for example, of tests, because and essentially the writing things up so that it still makes sense if one has this basic model behind everything. So there are different ways to write it, and this week I'm favoring this way, so that it's clear that the probability distribution of the test outcome is actually given, this actually follows directly. If we have a fixed theta, then the distribution of the data determines the distribution of these test outcomes. For example, the outcome, to make this explicit, test rejects the null hypothesis, for example. So this event here, this phi y equals 1 is an event. So this refers to the omega in omega, which are mapped to 1 by this concatenated mapping of the data sample and the test. It's just one has to think, if one frames these things in probability theoretic terms, then random variables are mappings, and then one always has to take care of from where to where they map and which distribution or which probability measures determine their distribution. And there is this the underlying family of probability measures here, which relate to this, which induce distributions. So remember that a distribution is the image measure of a random variable, and then statements like the test, so theta y equals 1, so the test says, in this case, reject the null hypothesis. This refers to this event, and this event is given if this is a random variable in terms of the omega and omega, which are met by this random variable, the combination of the test and the data sample to 1. The reason why this is important is, of course, if we look at the multiple testing problem and how the family-wise error rate is defined there. So the statistical test 0 to 1, and of course these two outcomes, so phi y omega equals 0, that's models not reject null hypothesis, no rejection, theta 0, although this is not meaningful, this is just the interpretation, so not reject the null hypothesis, and this means reject the null hypothesis. This is just what it models. Yeah? So one is the technical framework, this is the technical framework, and this is the thing that it models, like all mathematical models model something. Good, and then we also already discussed that we have errors. So if theta, the true but unknown parameter, is in theta 0, so the null hypothesis is true, and the test comes out theta y omega equals 1, then this is called type 1 error. So if the null hypothesis is rejected, if it is in fact true, this is called a type 1 error. And we discussed that there's also type 2 error, so if it's not rejected when it is in fact false, but nobody is interested in type 2 errors, or it's a little bit tricky with type 2 errors, because for some tests they are optimally minimal, and that is known, but then in general people are more crazy about type 1 errors but talk about power all the time, so it's a little bit weird what's going on, but in any case, type 1 errors are of concern for the single test error rate and also for the family-wise error rate. So, single test error rate, also we've seen that, so that's the single test error rate. So, the single test error rate is specified for theta in theta 0, meaning if you want to interpret this, that the null hypothesis is true, so the true but unknown parameter is an element of the null hypothesis, and then the single test error rate is for this test and for this parameter the probability evaluated under the probability measure given by the parameter. So this you can interpret as the probability distribution given that the null hypothesis, not given, but under the condition that the null hypothesis is true. It's the distribution of the data, and the event of interest is that the test comes out 1, so the null hypothesis rejected. So if you are thinking more in terms of measure theoretic probability theory, you might want to put some curly brackets around that, so that it's clear that this is a set, namely the omega, as we've seen above, the omega which are mapped here by this combination of one random variable and a deterministic function onto 1. So that's the single test error rate. So the probability for the test to come out 1, saying reject the null hypothesis if the null hypothesis is true. And then there's this thing of stair control, single test error rate control, which we've also seen. Namely, for a given significance level, alpha in this thing. A test is set to control the stair, the single test error rate, at a significance level alpha if the single test error rate phi theta is smaller than alpha, and now it's important, for all theta in theta 0. Yeah, so the single test error rate is defined for a single theta in theta 0. Of course, the typical thing is, or one very common thing is that you have this simple hypothesis that the null hypothesis only has one value, for example 0, and this is the distribution of the data of the test that acts on the data. If the true binomial parameter is 0, but this this of course allows also for larger null hypothesis tests, and if there's a larger null hypothesis test, for example, a larger null hypothesis set, sorry, for example, all negative numbers, then the single test error rate control is issued if this holds for all theta in theta 0. Good. So again, single test error rate is the probability of a type 1 error, and it's said to be controlled at a significance level if this probability is smaller than, for example, 0.05. for all values that the parameter can take under the null hypothesis. Then we discussed also last time Neyman person type tests, and I don't think I want to go over all the details again. So these are these tests. Now I have to do a little bit. These are these tests that we all know, and the most crucial thing is that they work in terms of yet another function, namely the test statistic, which takes values in the data space and maps them onto real numbers. And one might want to write this like this, but there are different ways to write this. So the important thing is that there are test statistics, and that one then can write the test. If one says that the test acts on omega, one can write the test in the form that phi acts on the transformation of the data by gamma and comes out 0 if gamma y omega is smaller than some critical value, and 1 if gamma y omega is larger than C alpha. Again, this is very familiar, but maybe looks a little bit strange. So what does it mean? The omega is selected under the original probability measure on the probability space. So this is where the randomness comes from. This is mapped onto some data by the data sample. So essentially this omega y just means you sample data y randomly. Then on the data, there is a real valued statistic. So you project the data, for example, in the GLM, the n-dimensional data vector. You project that onto a real value, meaning a single number, for example, the t value. By first computing, again, the expectation parameter estimate, the variance parameter estimate, and then evaluating the t formula. So you map that onto a real value. This is this gamma y, and then based on this real value that you evaluated, you decide whether the test is whether you reject the null hypothesis, or so whether you don't reject the null hypothesis, which is a 0, or whether you reject the null hypothesis, and this you base on the a critical alpha, on a critical value, for example 2 or 1.96 if you are want to make sure that the probability of a type 1 error is smaller than 0.25 if you go in this direction. Yeah, so this is just trying to generalize what and trying to abstract. So basically trying to just take the defining features of these procedures without going into the details that you what you actually do. Good. There are some other criteria for Nyman Pearson type tests that we already looked at it last time. So there's this monotonicity condition, which is this thing that the probability under the alternative for being larger than some critical value is larger than the probability under the null hypothesis. I put in another condition, namely that the rejection regions are nested. So this refers to the fact that so if you have a t distribution and you have one alpha which is smaller than alpha prime, then one rejection region you have here, gamma alpha prime. If you want now a smaller alpha, so for example going from 0.1 to 0.03 or something, or 0.05, then the other gamma is the other rejection region is nested in, so it's a subset of this. So oops, YF. Gamma alpha is a subset of gamma alpha prime. So this is also what's happening in all t-tests and z-tests and f-tests. Good. And then there's this final thing that I've been struggling with a bit because it's so obvious, but to actually show that this is the case is it feels a little bit redundant, but the thing that you, of course, in these Nyman Pearson type tests, you can, instead of making this decision based on the test statistic and comparing that to the critical value, you can also make this decision based on the t-value and based on the p-value, based on the p-value and comparing that to the significance level. Yeah, so if everybody knows that, but somehow I really struggle to frame that, and you also don't find that anywhere, to frame that a little bit more formally, that if that it's the same thing. So if you do take as a p-value for a data sample, you take the probability for the test statistic gamma y acting on the random variable y being larger than the test statistic evaluated for the data. So this is an observed data point, this is an observed data point, and this is the probability for the data to assume a value larger than the observed test statistic, which of course that's always what p-values were about. If you take this under these all these conditions for Nyman Pearson tests, then of course you can either do your test decision based on that the p-value is smaller than alpha. So you look at the p-value, and if it's smaller than 0.05, you reject the null hypothesis. Not surprising, everybody does that, and everybody's happy if the p-value that they compute is 0.049, then they are yeah. And but this is the same as finding that the critical value, that the test statistic of the data is larger than the critical value. This is completely trivial if you did undergrad psychology statistic, but it of course only works because these are fairly specific tests where these things nicely go hand in hand, and everything is basically looking at situations as this. Yeah, and I'm still struggling to actually really clarify for myself what that actually means. That whether it's some events that are identical, or whether one should say, if one does it like this, if one uses this approach, then one controls the single test error rate, as one does in the test when one uses this. So somehow I'm a little bit fuzzy there, because, and it's also not the most fun thing to do because it's so obvious. If p is smaller than 0.05, then you reject the null hypothesis, and that's the same as finding that the critical that the test statistic is larger than the critical value. So I'm a little bit struggling with that part, but yeah. But I think for everyone it should be fairly obvious. So that was a brief run through the single test case. Now we just keep going to the multiple test case. Good. Multiple testing. So now that we have the single test scenario and test fairly defined, we can talk about, or family defined, we can talk about a multiple testing problem. And that is again given by some data outcome space with an associated sigma algebra. Again, a family of probability distributions that are defined in terms of the data sample, which is this one variable y, and a family of probability measures, and a set of hypotheses, like this. And now the crucial difference between a single test problem and a multiple testing problem is that this set of hypotheses, trying to do this calligraphic H here, is not a single null hypothesis, but many. And that's how one can do that. So I is an arbitrary index set. So now what's an example, or how can one think about this? Of course, what we have in mind is that there are many voxels and we have to control somehow, or adjust the p-values or whatever, but what one different way to think about it is that the data that is realized is a whole random field in 3D. So infinitely many data points essentially, and then we can have infinitely many null hypotheses which can be framed in the sense that the expectation of this random field at location x is 0, and it's something else on all of the other locations, and then you can shift essentially the 0 assumption through the entire space, and then you have infinitely many null hypotheses because each of them form a specific subset of the parameter space. If you think in terms of the parameter space being the expectation function of the random fields. So a function, I can write a little bit about this. So if you have this mu and it's R3 to R, then one null hypothesis would be that how can we do it? Maybe let's do that in 2D, then it's easier. So let this be the real line and this also the real line, and then one null hypothesis could be that at this location here the parameter is 0 and it's something else everywhere else. This is the problem, is that one never, this would really make it require some effort to fully write that up, what how this actually looks. But the idea is, of course, that you because you have these many possibilities where you can have something 0, then you also have so one null hypothesis. Let's I haven't prepared that, so I'm making this up on the fly. Let's go to 1D. That's easier. The real line, and one null hypothesis could be that exactly here at xi the expectation is 0, and everywhere else it's some arbitrary number. So this is not really making sense. I'm not getting wrong with that. It's actually sorry. I have one example that I made up which makes a little bit more sense if one frames the whole thing in terms of the GLM and writes this up, but it's not. We have many null hypotheses. Let's keep it at that. We have many null hypotheses, and at present I'm not really good at giving a nice example for it. But we have many null hypotheses. And typically we have not infinitely many, as I'm just trying to explain, but we have a finite number of null hypotheses. And this is the case if we talk about voxels, then we have let's say n voxels. And the problem is then that at each voxel we want to test the null hypothesis that at this location the expectation is 0, and we do that for all of the different locations, and then we have the set of null hypotheses. Yeah? But the whole thing is also fairly arbitrary. This is also what I'm trying to say. So the multiple testing scenario, it's never quite clear, or I mean, you have to. There is no natural set of null hypotheses. Yeah? This is the same thing that you never know whether you should correct for all t-tests you did in your life, or for all t-tests you did in the last 2 hours, or for all t-tests you might do in the future, and so on. So this is all not clear and depends on a given of what you want to protect yourself against in a given context. So this whole multiple testing, although people get really anxious about it and quite, we all have to do correction for multiple testing and so on, it's not really clear what the family of null hypothesis is. This is just a convention. I mean, in fMRI, everybody, this is also completely strange in fMRI. In fMRI, everybody is so concerned about the many boxes. There are so many boxes. We have to correct for that. And then everybody does multiple contrasts on their data. So testing null hypothesis in terms of one beta parameter, next beta parameter, next beta parameter. And this is not of a concern for multiple testing, which makes more or less no sense, because that's what people in terms of multiple comparisons when they do ANOVA, what they always talk about. So this is very there's a very sociological conventional what the important set of null hypothesis is. But if for some reason some people have decided of what the set of null hypothesis is, then one can define a multiple test. I think here's getting slow. This under a multiple testing scenario is a mapping for which I now take the big phi from omega to the Cartesian product of the set 0, 1. Oops. And for each omega, this multiple testing acts again on the data. Yeah, so if you think in terms of brain analysis, you get this realization of the data, which is a 3D volume, and then you act with your multiple testing procedure, you act on the whole thing. And what what the thing then is, what you do is that you apply these single tests to the data, and you apply actually one single test for each null hypothesis. So I'm just taking the Cartesian product here. It could also, if you have a finite number of null hypotheses, you could also, of course, take the 0, 1 to the power of n instead of having something infinitely large. The reason why I was interested in this infinitely many numbers, because in random field theory, the support is, of course, you don't have 40,000 voxels in a random field. You have infinitely many support points. So you actually, if you're using the maximum statistic for multiple testing, the multiple testing problem is actually specified in terms of your random field, and there you don't have 40,000 voxels, but you have infinitely many voxels. So this is why I try to frame the whole thing not in terms of a finite set of indices or finite set of multiple tests, but an infinite set of multiple tests. The important thing, however, is that this multiple test is essentially is a procedure that acts on the data. And it essentially comes down to a vector of many single tests, which is also not surprising. I mean, this is what you do in brain imaging and data analysis. You have a realization of the whole data, which is your brain volume, and then you apply, for example, 40,000 single t-tests, and then this is your multiple testing procedure, or your multiple test. Yeah, because the family-wise error rate, of course, relates to the multiple test procedure, and this is what we now want to talk about. So if things are a little bit simpler in terms of that you have not talking about an infinite index set, but a finite index set, then of course one can think about it as that one has some data y, and then one applies a multiple testing procedure to this data, and one outcome of that is, of course, then a long vector of zeros and ones. Where each of these is the outcome of a individually phi I. Yeah, so this is what this should be. If you are dealing with finite sets. Now, what is the family-wise error rate? Maybe I should write it out. Maybe I should stop the recording and restart it because it's getting really slow.